Alright, today we're going to look at sections 1.5 and 1.6 and finish off chapter 1. 1.5 is inverse functions, 1.6 is variation. So we want to further understand inverses. We have already talked about this some, so this should be review. And we want to understand variation and modeling as well. So first, our formal definition of the inverse of a function. So let f and g be two functions such that f of g of x equals x for every x in the domain of g, and g of f of x equals x for every x in the domain of f. If this is the case, then, so let's see, the book says it like this: under these conditions, then the function g is the inverse of the function f. And so if we use our function notation, that's saying that g equals f inverse. So remember this little function to the -1, that means inverse. Also, if this is true, if g is the inverse of f, then f equals the inverse of g. Now, in order for this to happen, or in order for two functions to be inverse, a few things, there need to be a few restrictions on the initial functions. And one of those is that the functions have to be what's called one-to-one. And what this means is that every element of the range corresponds to exactly one element of the domain. And so this needs to happen in order for a function to have an inverse. If it does not, then we have to restrict that initial domain somehow. Another thing or another relationship, I should say, between a function and its inverse is the relationship between the domain and the range. So the domain of, let's say, our function f must equal the range of f inverse. And the opposite is also true. The range of f must equal the domain of f inverse. So those also have to be true in order for the functions to be inverses of each other. In order for a function to have an inverse, sometimes we might have to restrict the domain. We have a test graphically to determine if a function will have an inverse. And you may remember this from a previous class. This is the horizontal line test. And basically what we're looking for with the horizontal line test is we draw a horizontal line. If that horizontal line crosses the function more than once, then it does not have an inverse. Again, sometimes we can restrict the domain of the original function so that that does still work, but that is our graphical test. And then you also might remember the relationship between a function and its inverse is graphically they reflect over the line y equals x. So that's a really easy way to graph an inverse of a function if you already have the original, then using this reflection property. Okay, so now let's look at an example for analytically determining if two functions are inverses. So if I have this function f of x equals x plus 3 over x minus 2 and g of x equals 2x plus 3 over x minus 1, I want you to just try and demonstrate analytically that these functions either are or are not inverses. So pause the video, and when you're finished and want to check your answer, then come back. Okay, so our analytical test, remember, is to actually do the composition of the two functions and see if it simplifies down to just x. This also is not a coincidence. It directly relates to the fact that they reflect over the line y equals x. So here you can see I've done first f of g of x. So I substitute the g of x function into the f of x function wherever there was an x. I multiplied the 3 by x minus 1 over x minus 1 to get a common denominator in the numerator, and I multiplied the negative 2 by x minus 1 over x minus 1 to get a common denominator in the denominator. Combine like terms and simplify. The x minus 1 in the numerator and denominator cancel. The 2x and the negative 2x cancel. The 3 and the negative 3 cancel. I'm left with 5x over 5. The 5 is reduced and I get just x. Now, I know that we're going to want to take shortcuts and we're going to want to say, okay, well it worked here, so I know that they're inverses of each other. And I'll be honest, most of the time that is going to be true. However, one, for practice and because I'm asking you to, and two, because it is not always true, we do need to check the other one as well. So we're going to do what is g of f of x. So I substitute the f of x function into the g of x function wherever there's an x. Again, get a common denominator in the numerator and in the denominator. Combine like terms. The x minus 2 in the numerator and denominator cancel. The x and the negative x in the denominator cancel. The 6 and the negative 6 cancel. And again, I'm left with 5x over 5, so it just reduces to x. Therefore, yes, these are inverses of each other. Okay, now we're going to talk about types of variation. The most common ones are direct, inverse, and joint, so those are the ones that we're going to talk about here. And this you hear a lot of times, the relationship between two things, something varies directly as something else, or inversely as something else, or jointly as something else. That's what we're talking about. The direct variation is just a linear model with a y-intercept of 0. And the generic equation is y equals kx. So we can see that's our linear model. Instead of m for the slope, we're using k. We'll talk about k in a minute. But so this would be that we would say, y is directly proportional to x. And if we're told that, then we know this model fits. So then inverse variation is going to be if we have y equals k over x. So that's our generic inverse model. And joint variation is saying that we have multiple variables. So this could be something like z equals kxy. So that's telling us z is jointly proportional to x and y. And so then now again, just to talk about k, and so this applies for all of them, k is what we call the constant of variation. Or you could say constant of proportionality. And so k is going to have some value that's going to change depending on what the actual relationship is between the variables that we're talking about. Also, another note, k doesn't equal 0. If k equaled 0, then this would not be variation. Okay, so now let's do a little bit of practice. So I'll do the first one with you, and then you guys can pause the video and try to do the next few. So we want to find a mathematical model for the following scenarios. So a varies directly as the square of r. So I'm going to say a equals k r squared. Be careful that when it says the square of r, it's talking about r squared, not the square root of r. If it was the square root, it would be specific about that. Okay, so now that you saw that, I want you to do the next three, so pause the video and then unpause it when you're ready to check your answers. Okay, so y varies inversely as the square of x is going to be y equals k over x squared. F varies directly as g and inversely as the square of r. So one thing at a time, f equals kg would be directly as g, and inversely as the square of r is going to be over r squared. Here, for a constant temperature, the pressure P of a gas is inversely proportional to the volume V of the gas. So based on the way that this sentence is written, you would probably want to write P equals little t over V, where little t is the constant now. So I switched up instead of using k, and you don't always have to use k. K is just kind of the standard. But in this case, since we're talking about temperature, I can use little t if I want instead. Or I could say V equals little t over P as well. Those are the exact same equation, just written in different orders. Again, this first one here, this is kind of how the sentence is saying it. But this also shows you now that there actually are a lot of practical applications to understanding different types of variation as they do relate to the physical environment around us. Okay, so let's do this last example. Neglecting air resistance, the distance as an object falls varies directly as the square of the duration of the fall. An object falls a distance of 144 feet in 3 seconds. How far will it fall in 5 seconds? So I want you to come up with the variation equation, solve for the constant of proportionality, and then answer the question, how far will it fall in 5 seconds? So pause the video and unpause when you're ready to check your answer. Okay, so our variation equation should be S equals kt squared, since an object, since S varies directly as the square of the time. So then if we plug in the 144 for S and the 3 for t, we can solve for k, and we get our constant of proportionality is 16. And then we want to find how far will it fall in 5 seconds, so I plug in the 16 and the 5, and I get 400 feet, and I answer in a little phrase or sentence, it falls 400 feet in 5 seconds. We should always answer word problems in a sentence to demonstrate to ourselves and to the reader that we understand what it is that we actually found. Okay, so to conclude, to find an inverse, we switch the x and y and solve for y. We didn't do an example like that, but we've done that before. Inverses only exist if they're one-to-one. Understand the relationship between the domain and the range of a function and its inverse. Graphically that they reflect, and then here are our variation equations.